Hi, I'm Doa from MIT CSAIL, and today I will present SensiCut, material-aware laser cutting using speckle imaging and deep learning. First, here's the question. What materials do you see here? They all look similar, but are they of the same type? They're actually completely different materials as you see here. SensiCut can sense and distinguish between these material types, and then set the correct laser power and speed values for cutting or engraving them, or even warn users if the chosen material is actually hazardous for laser cutting. To clarify our motivation, let me start by explaining the common laser cutting workflow today. When a user wants to laser cut a design, they first select the material from stockpiles or scraps in a shared workshop, such as this one in our lab, where our postdoc Isabel is looking for a piece of extruded acrylic. As you see in this real-life example, these materials are often left unlabeled, unfortunately, or may be hard to distinguish for those that look similar. After picking the sheet, you would then launch the laser cutter software, and hopefully make an educated guess and select the correct material name from a big database. Now, if you choose the correct one, that is great. But in reality, it's tough to get it right the first time, especially if you're not an expert. So what happens if it goes wrong? Well, the best case scenario is you haven't applied enough laser power yet, so the outline is not cut through yet. So you may put it back in the laser cutter, try to align the sheet at the same position, and apply the laser again. More concerning is that you may have chosen a material like PVC that is not intended for laser cutting, as it releases toxic fumes when laser is applied to it. And perhaps the worst scenario, the laser power is too high for the material and the workshop is set on fire. As you can imagine, these possibilities not only raise the entry barrier to laser cutting for beginners, but also, even for expert users, differentiating between visually similar workshop materials you see here, including those that are suitable or unsuitable for laser cutting, remains an obstacle. Thus, laser cutter users want smarter machines that can identify the materials they are working with, so that the system can suggest settings based on material, as shown in a CHI 2020 study. Now that we know the problem, let me explain what solutions have been proposed so far. The first solution that comes to mind is adding a camera to the laser cutter so that it can automatically identify the sheet. However, a single camera can be easily fooled by cases like this one where the sheets have the same color, but require completely different laser settings. Alternatively, we could measure the retroreflective properties of different materials to more accurately distinguish between them. But such systems often require bulky hardware. Another solution is to attach sticker tags to individual sheets, such as this QR code you see here. However, during laser cutting, if the code is cut off from the main sheet, it cannot be identified in future uses. Also, if an incorrect tag is attached, the laser cutter will assume the wrong material type. In short, previous work includes naive camera-based approaches that may not be robust or require the use of bulky hardware or cumbersome tag-based approaches. In our work, we intend to identify materials by leveraging their inherent properties to overcome these issues. We do this by using an optical method called laser speckle imaging, which helps us sense the surface's microstructure. Speckle imaging works by pointing a laser onto the material, so that the laser interacts with the very tiny features of the surface, which you see at the bottom. When the light source is on, it emits the laser beam, marked green here, and these rays are reflected off the surface, arriving at the pixels of the image sensor on the top right. Now, phase differences between these rays cause mutual interference at each pixel of the sensor, causing either destructive or constructive interference, shown here as dark and bright pixels. As a result, we get this 2D image. When I was first experimenting with this technique, I took pictures like this one, with a regular camera which has an optical lens. So we see that the green laser appears as a small dot on the surface in this picture. And here's a zoomed in version of the same setup, which shows us the speckle pattern much better. However, it is still present in only a small portion of the whole photo. This is because the lens of the camera directs not just the laser light, but all the available light rays in the scene onto the image sensor. And this gives us less speckle data to work with. I noticed when you remove the lens from the camera though, it is only the reflected laser light that lands on the image sensor. Thus, the resolution of the speckle is as large as the entire image. And this gave us a much clearer high resolution pattern. Here, you see this in action. The camera has no lens, so we see nothing in regular lighting. But when you turn on the laser pointer, we see the speckles in great detail. In short, the distribution of these patterns are distinct for each surface, and therefore lets us easily classify the material. To make this more clear, I actually went into a material science imaging lab and used a scanning electron microscope to get these micron scale images you see in the middle, which really shows how different materials actually are. We used this speckle imaging technique inside a laser cutter, for which we had to create a mountable setup. As you see here, our imaging add-on can be attached onto Laserhead very quickly. And it consists of low-cost, off-the-shelf components, as you see here. To make it compact, we designed and 3D printed a lightweight mechanical housing. Altogether, the attachment weighs only 114 grams. In the future, this additional laser pointer may not be necessary, since most cutters, commercial cutters already have one, which can be repurposed for our imaging method. Similarly, other components like the battery and the microprocessor can all be fully integrated in future fabrication tools, which already have an energy supply and processing hardware. This makes our method particularly easy to integrate with laser cutters. So now that we know more about this technology, I would like to talk about the user interface we have built for it, and what kind of applications we can use it for. In the first example, my lab mate Isabel wants to rapidly prototype a new earring design, and test the look and feel of different materials for it. Designers often use material swatches consisting of different samples to get a sense of what material would work best for a design. In this example, Isabel picks 4 samples from a swatch that may work well for the earring design. She then places these on the laser cutter bed and loads the design file in the UI. Next, she chooses the Scan Multiple Sheets option. Sensicut then captures the speckle pattern for each shape and predicts the corresponding material type using our algorithm. You can see these results in the right sidebar, where each color represents a unique material, in this case felt, foam board, cast acrylic, and leather. And we see these shapes on the left are colored according to this detection. After entering the thickness values, Isabel starts the cutting process. And here you see the finished earring prototypes. In our final use case, I would like to show you an application very common among laser cutter users. Many of us often engrave custom designs, such as text or patterns, on our everyday belongings. With Sensicut, we can take this one step further and engrave objects that consist of different materials across its surface. This phone case looks as if it had leather and wooden parts on its surface. However, the woodlook part is actually made out of rubber, which may not look obvious in a camera image. To detect these materials, we select Scan Multi-Material Objects this time. In this mode, Sensicut automatically samples points along the shape's outline, and captures the speckle patterns at these points. Once complete, our UI automatically partitions the shapes into material-specific paths and assigns them the correct laser settings. And here's the final result. So let me conclude. Many laser cutting materials look similar, and additionally, many hazardous materials are often confused for safe ones. Sensicut senses the sheet's unique surface structure using speckle imaging, and this enables us to select the correct laser cutting settings, and new applications such as precisely engraving multi-material objects. Now, let me zoom out a little bit and talk about what's next for this work on identification and tagging. My bigger vision is to enable users to more unobtrusively identify things in our surroundings, so that they can access and retrieve more information related to them quickly and seamlessly using physical tags. I distinguish between 2 types of tags here, natural tags and engineered tags. Sensicut is a great example for natural tags, which are basically existing physical features of objects and materials. In comparison, engineered tags enable us to define the type of information or pattern we want to embed on an object during the fabrication process. An example is my Kai 2020 project, GID, which uses the subtle patterns left by 3D printers to distinguish and identify objects that otherwise look similar to the human eye. As future work, I'm planning to build new systems that can leverage the advantages of both methods. Thank you so much for your time, and I'm happy to answer your questions.